So two simple problems with Faraday's law. Here's number one. First problem, and see what it says. We have a circular coil of wire has a radius diameter of 20 centimeters. Now that means that I have R being 0.1 of a meter. And from here I can easily calculate the area. If the radius of a circle is 0.1 of a meter, then the area is just pi r squared. That would be 0.0314 meters squared. Let me pause for a second, make sure that this is actually correct. All right, so that is true. So we have area, but we have 600 turns. That would be n equals 600 turns, 600 loops. And this thing is placed in a uniform magnetic field of 2 Teslas. So the magnetic field B is 2 Teslas, and it says uniform, so that means B is not changing. The direction of the magnetic field makes an angle of 60 degrees with respect to the area of the loop. So I'm going to draw this again, and I'll take a specific approach to it. Although I'm not sure if these problems are clear enough in that sense. But anyways, here's the magnetic field B. And then let's say that the loop is pointing like this, so that the wire comes out of the page on the top and then goes down and then goes to the page on the bottom. This is the wire. So it goes, and then here's the A vector. I frequently use red for it, so let's continue with that. So here's the A vector, and that's at 90 degrees to the surface of the loop. And the angle that is given to me is, I'm going to say that the angle is, let's see, the direction of the magnetic field, the direction the magnetic field makes, the direction of the magnetic field makes an angle of 60 degrees with respect to the area of the loop. So I think it's actually this. This is 60 degrees here. Which means that the angle that I actually need, theta, is, I write this here, theta is just 30 degrees. And what else do I have? The coil is suddenly pulled out of the field in 2.3 seconds. So what happens is we have, let's show it from a different perspective, so that we have the magnetic field, let's say, pointing into the page. So it's the same thing, but now from a different perspective. We're looking at the loop here. It's sitting in the magnetic field, and then an instant later, this thing is pulled out and it sits outside of the magnetic field here. Right, so this is what we have, some speed v. Now this happens in 2.3 seconds. So the actual time in which this thing is pulled out is 2.3 seconds. I'm going to write here that time delta t is 2.3 seconds. So what is it that is changing? Well, I could say that the magnetic field goes from the initial value of 2t to the final value of 0t, and that would be true. Or I could approach it a little differently, and this is in fact what I'll do. Both cases, both approaches would give the same answer. I could say that initially I have an area of 0.0314 meters squared present in a loop, and then the final area present in this is the area of the loop present in the magnetic field, and then the final area of the loop present in the magnetic field is 0 meters squared. There is no area present in the magnetic field at the end. So I could take this approach, and this is what I'll do. And so this will give me delta A. All right, and what else do I have there? I have the resistance R. Let's put this here. Resistance R is 100 ohms. And the question is, what is the current? What is the voltage and what is the current? So the unknowns, let's state the unknowns. Maybe I'll put them here. Unknowns are the EMF is the unknown, and the current I is the unknown. Well, let's calculate the EMF. So the equation is minus n times the change of the magnetic flux over the time. And so I have minus 600 for n times the change of A, B cosine theta over delta t, what's changing is the area. At least that's how I set up the problem. And so what I'm going to have here is minus 600 times the change of the area. I go from 0 to that, so I end up with, well, let's just write this 0 minus 0.0314, and I'm running out of space. I guess I'm going to slide this screen, times magnetic field, which was 2, times the cosine of 30. All of this divided by the time, which was 2.3. So what I have then is minus 600 times minus 0.0314 times 2 times the cosine of 30 divided by 2.3. And so epsilon, or EMF, equals, and note that you could have done the same thing by saying that it's the magnetic field that changes. You would have ended up with the same correct answer. But in the meantime, what I get for the answer is I get 14.2 volts. What I get. And from here, it should be pretty easy to calculate the current. I equals EMF, or voltage, divided by the resistance R. And in this case, it would be 14.2 divided by 100. So that gives me 0.142 amps. All right, now let's look at the second problem. Bring this thing back. The second problem says a circular coil of wire has 300 turns. So let's do it here, number 2. 400 turns, so N is 400. I have the diameter, which means R is 300 centimeters. So that means that the radius is 150 centimeters, so this is 1.5 meters, and from here I can get the area. A equals, so 7.1 meters squared. And then what else do I have? It is placed in the uniform magnetic field. Okay, B is constant. The direction of the magnetic field makes the angle. Oh, so what changes here is the angle. So the initial angle direction of the magnetic field makes an initial angle of 0 with respect to the area of the loop. So what I should do is I should probably draw a picture with it, so that what I have is the magnetic field that points to the right, and then I have the loop. I'm going to draw the loop like this. The wire comes out of the page and it loops downwards and goes into the page, right, and comes back up again. So there's my loop, and here's the A vector, points like this, 90 degrees. And what the problem is given me is the angle here, and that angle is 0 at first. I probably should have drawn it a little differently. Yeah, well, let's just draw it a little differently. So what I'm going to do is I'm going to redraw it. I'm going to redraw it right here, so the magnetic field points to the right. And initially what I have is, so this, we'll just cross this thing out. Or maybe I'll keep it there. So the loop is pointing like that. In other words, it comes out of the page here. I could actually probably, this one is easy enough where I can draw this in 3D. So this is, there's that, and then A points like this. So the initial angle, they say it is 0 between the magnetic field B and the loop itself. So that means the two are parallel, and that implies that the angle between A and B is going to be 90. So theta I is 90 degrees, and then this thing rotates in half a second. So let's state that this thing rotates in half a second, and the initial angle is 90. So this thing rotates in half a second to the angle of, what do we have there? area of the loop, and then it rotates at an angle of 60 degrees. I guess I could just keep this so that this was going to refer to the initial and this is going to refer to the final. And so then what I have is 60 degrees right here. So this is 60 degrees, and therefore the angle that I actually need, which is theta f here, that would be 30. Right, and so what I have here is that theta f is 30 degrees. And let me pause and reread the problem, make sure that this is actually what the problem is talking about. Okay, so we're good. And then we have the magnitude of the magnetic field being 2 teslas, 2t. And I think that's about it. Well, we have the resistance as well. So let's state that the resistance is 100 ohms. And the unknowns are the EMF again and the current again. And so we can solve this problem here. EMF is going to be, well, we might actually need a little more space than that, but let's pull this up. For that matter, let's just do it here. So EMF equals minus n times the change of the flux with respect to time. That amounts to minus 400 times the change of A times B times the cosine of the angle theta, because that's the equation for the flux. This divided by the time, so negative 400 times. Well, what's changing is the A and B are constant. So A times B comes out, and I have the delta of the function cosine theta divided by the time. Let's plug some of this in. Minus 400 times area A was 7.1 times the magnetic field 2, and then times the cosine of theta f minus cosine of theta I. This here divided by the time in which the change took place, which is 0.5 of a second. And so the EMF equals, let's plug all of the numbers in. So minus 400 times 7.1 times 2 divided by 0.5 times the cosine of the final angle was 30 degrees. The initial angle was 90 equals. So let's calculate this, see what we get. And so apparently what I get is minus 9,838 volts. Okay. So this would be the voltage that I would get out of this setup. And that's a lot of volts, and then the current I would be the voltage or EMF over R. And so in this specific case, it would be minus, keep the minus, but don't worry about it. We'll look into that with another video. So 1938 volts divided by the resistance, which was 100. And so that gives me minus 98.38 amps. That's also a lot of amperage. But anyways, so now we've solved two sample problems. And you should be comfortable solving all the other problems on the worksheet that you have there for the Faraday's law.